So we're going to get into the into Fourier series. Really, this is the beginning. This is, I think, lecture 3 or something of the lectures that I give in my Fourier series class. Usually, whenever I get the chance to run it, which is almost never. But lectures 1 and 2 are basically review of the stuff in 131. Okay, so let me just give a couple things that that were not in 131, but that you could use that you're going to need. So notions that you're going to need. So introduction to Fourier analysis. Okay, so all sorts of stuff that you've seen before. So background material, most of it you've seen before. The two things that you haven't seen before are, one, the notion of measure zero, and two, Fubini's theorem, which you may have seen. Okay, so measure zero is a kind of way of, it's a notion of smallness for sets. Okay, like you can say that this set is really, really small. That's basically what being measure zero is. Like, this set is small. Okay, so here's the definition. We're not going to say too much about it. So you have a set in R is said to be of measure zero if given any epsilon greater than 0, there exists a countable family of open intervals. And I realized, so this is taken from Stein, the book of Stein and Shikarchi, called Fourier Analysis. It's book 1 of their lectures of the Princeton Lectures in Analysis. And I realized that Stein is using the term countable to mean either finite or countable, what Rudin calls at most countable. Okay, so maybe I should say at most countable. So your measure zero, if given any epsilon, there's a countable family of open intervals, I sub k, such that one, E is covered by the union of the I sub k, and 2, the sum of the lengths of the I sub k's is less than epsilon. So this is what being measure zero means. Okay, so of course, right? If I have one point here, x, right? If my set is just a single point, right? Then it's going to be measure zero, right? Because I can cover it. Given any epsilon, I'm just going to cover this first guy with an interval of length smaller than epsilon, right? You guys, should I slow down? You guys are copying? Still copying. Okay, so right, if there's just a single point, right, or if there's a finite number of points, right? Suppose there, or if there's a countable number of points, it's still measure zero. Okay, right. So notice that E countable implies that E is measure zero. Right, because if E is x1, x2, x3, dot, 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 right, then you just say, I'm going to cover the first guy with an interval of length epsilon over 2. You cover the second guy with an interval of length epsilon over 4. The third guy with an interval of length epsilon over 8, and so on and so forth, right? You add up all those lengths, it's less than epsilon, right? The sum of all those lengths, right? Epsilon over 4 right? Epsilon over 2 plus epsilon over 4 plus blah, 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 is going to be less than epsilon, basically. Okay, so so any countable set is measure 0. Does that make sense? Okay. Okay. So right. Basically, it means that you can cover the whole set with as little material as you feel like. Right. If somebody says, "Can you cover this set with material of length 1?" Yeah, you can. Can you cover it with material of length 1/2? You can. Whatever epsilon you're given, you can cover that interval with that amount of material. So that's kind of interesting, right? Because what that says is that the rational numbers don't take up very much space, right? If you think about the rationals in R, right? How much material do you need to cover all of R? Well, you need an infinite amount of material to cover all of R. But to cover the rational numbers in it, you need basically 0 material, right? As little, you can cover it with as little material as you desire, right? What that's saying is that statistically, probabilistically, the chance of you choosing a random number by accident is 0, right? Choosing a rational number randomly is 0. Okay, that they're very, very sparse within the reals. Okay, okay. So lemma. The union of countably many sets of measure 0 is still measure 0. Okay. And there's a theorem that we're not going to use now, but let me just tell it to you. A bounded function is integrable. A bounded function is Riemann integrable if and only if the set of discontinuities is measure 0. Okay, so there's a nice characterization of Riemann integrability. I think this is called Sard's theorem.
Is being a measure 0 in some sense the same as being discrete? Because discrete and continuous.
What does discrete mean?
Like in there we only have like some points instead of like intervals. Like discrete.
Yeah, I mean, you can have an uncountable measure 0 set. For example, the Cantor set is measure 0, but it's uncountable. So it's not the same thing as countability, if that's what you're asking. I'm not. Somebody asked me a question earlier in this term about discreteness, and I'm not really sure what discrete. But
not continuous.
Yeah. Continuous. What opposites? No. So I mean, it's true that if there's any sort of interval in there, right, if there's any sort of continuous interval, then that's not going to be measure 0, right? Because there's no way you can cover that interval with materials shorter than it, right? So maybe that answers your question. Okay. One result that we will use is so-called Fubini's theorem about changing the order of integration. So, so if f is a, and we're not going to define this term, measurable function, For that, you have to wait till some of the course. If f is a measurable function such that its double integral is finite, then you can change the order of integration, and this give the same result. Okay, so this is just saying that it's okay to integrate with respect to y, x first and then y, or y first and then x, under certain conditions. Okay. Okay. So it's not true in general. Okay. So in general, it's not okay to do this. You might think, oh, it's okay to just change the order of integration, but there are counterexamples where you change the order of integration, and one integral gives you 0, the other integral gives you 1, or something like that. So there's an example on Rudin's red book, so real and complex analysis. Right. This is the Rudin to your book's Baby Rudin, right? People call the book that you're using Baby Rudin, and they call this book Rudin. Okay, so I think I told you that, right?
Yeah.
This book's called. Yeah. Now that you've been through it, you say, oh yeah, we took a course in Baby Rudin. Okay. On page 166, there's a counterexample showing that if you change the order, then you can get different answers. Okay. 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 Okay, so now let's get to it. Introduction to Fourier series. Okay. So So, actually, one thing, let me just mention one thing that I'm not sure if we're going to use, but let me just introduce it now anyway. So, if you have some function, sometimes we'll talk about functions on the circle. Okay. If I ever say functions on the circle, if I ever say functions on the circle, what I mean is that it is a 2 pi periodic function on R. Okay, so that is, right, you've got some function and, it repeats, right? It takes its values between, its arguments are between 0 and 2 pi, the angles of your circle, right? The angles of your circle, and it repeats. Okay, just like if you're going on the circle, right? If you went around, then you, right? So when I say this, I mean a 2 pi periodic function. Okay. So now let's give the real definition. Okay. So given an integrable function f on some interval ab into the complex numbers, we define the Fourier series of f as something like this. Fn hat e to the 2 pi I n x over L, where L is b minus a, and n goes from negative infinity to positive infinity. Where these f n hat are defined like this. You take the integral of f against e to the negative 2 pi I n x over L and divide by L.
Sorry, what is I? You said 2 pi I n?
I is the imaginary, the square root of negative 1 from the complex numbers. So these guys denote what's called the nth Fourier coefficient. Of f for n. Okay, and I'll explain things I'll explain everything.
What's the exponential?
Negative 2 pi I n x.
Negative?
Yeah, negative.
But not that.
Not in this one. Not in this one. Okay. Okay, so the first question you should have is, what is this e to the complex number, right? But maybe you should not have that question. What should that be? So what do we mean by e to the z, where z is a complex number? Well, we just, for the real numbers, you have a power series expansion for e to the x, right? It's this, x to the n over n factorial, right? And from 0 to infinity. So recall this power series expansion of e, right? So that's on the real line, but the real line sits inside the imaginary plane, the complex plane, right? And so what we're going to do is we're going to use this definition and just use it as the definition of e to the z. So we define for z in complex numbers e to the z as summation z to the n over n factorial from 0 to infinity. Okay. What's the radius of convergence? We define it in terms of a power series. What's the radius of convergence?
Infinity. Is it infinity?
It's infinity. Why is it infinity? Why is it infinite?
Because if you do the ratio test.
Yeah, do the ratio test. You say, well, let's take the limit of the n plus 1th term divided by the nth term, right? Right. We want that to be, as long as that's smaller than 1, then this thing converges, right? Right. So this, the series power series converges as long as this thing is smaller than 1. And you see what happens, right? The z to the n cancels out the z to the n. You pull out a z, right? And no, let's not pull out a z. Right? You get this over n plus 1 as n goes to infinity, right? Which is 0. So you know that whatever z you use, this is going to converge. right? Okay, and in exactly the same way, you can talk about the sine of z or the cosine of z, right? The sine of z is going to be z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus plus, etc. This is going to be 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus plus, etc. So similarly, you can define sine and cosine for complex numbers. Okay. And you notice that if you take cosine of some number, theta, plus I sine So, sorry, you notice that if I take e to the I theta, say, right? If I take e to the I theta, what's that going to be? That's going to be 1 plus I theta squared over 2 factorial plus I theta cubed over 3 factorial plus I theta to the 4th over 4 factorial plus blah, blah, blah. Right? So that's going to give me this 1 plus I theta plus negative. This is going to be negative I theta cubed over 3 factorial plus theta to the 4th over 4 factorial, etc., etc. Right? And maybe you see what's going on. If I look at the real part of that, what's that? The real part is going to be 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial, etc., which is the cosine, right? And if I look at the imaginary part, you see that I get the sine, right? So you get cosine theta plus I sine theta. Okay, so this is so-called Euler's formula. Okay, and another thing that you notice is that if I take e to the minus I theta, I'm going to get cosine of negative theta plus I sine of negative theta, right? But cosine theta is an even function, right? Because it's got all these squares in it. Right? And so this is just cosine theta. And sine is an odd function, so I get minus I sine theta. Right? Okay. So this is e to the I theta, this is e to the minus I theta, right? And you see that if you add the two together and divide by 2, you get the cosine, right? So e to the I theta plus e to the minus I theta over 2 is the cosine. Right? And if you subtract e to the I theta minus e to the minus I theta, and you divide by 2i, you get the sine. some of you have probably seen this already. For those of you who haven't, are there any questions? I'm just trying to, the Fourier series are expressed in terms of these, exponential functions. So just to make you more comfortable with exponential functions, let's do this part. Yeah.
It's a generic question. Will we be tested on this?
You'll be tested on parts of it. Yeah.
Fourier analysis.
So there are parts of this that will be very relevant to what we've been doing before. So yes, that's fair game. Okay. Okay. So let's get back to this thing here, right? So you take a function. Right? You take a function, and then you take your function and you integrate it against a certain frequency, right? So you want to think of these guys as, this e, is related to the trigonometric functions. Okay, you think of this as some sort of frequency. The n, right? As the n increases, your frequency, increases basically. Okay, so you integrate it against a certain frequency, and you get some number off of that. Okay, right? You integrate against 2 pi I n x over L, and that's going to give you the nth Fourier coefficient. Okay. Okay. So you take your function, you integrate it against different frequencies of e. You get this number off of it, and then you use those numbers as coefficients. You use those numbers as coefficients to create this infinite series. Okay, and this thing is called the Fourier series. Okay, what you want to think about, is going back to linear algebra. That basically what you're doing is you're taking your function and you're trying to express it as a linear combination of these guys. Okay, you're expressing it as a linear combination of these guys, and there's some way of getting the coefficients. Right? There's some way of getting the coefficients that allow you to reconstruct your function. Okay, so. Okay, so okay. Okay, so one remark. There's no guarantee. There's no guarantee that the Fourier series converges. Okay, there's no guarantee that this thing is going to converge. Even if it does converge, there's no guarantee that it converges back to F. Okay. In fact, why are you smiling? Okay, anyway, in fact, so why do we care? Why do we? Okay, hold on. So let me say something a bit worse, and then I'll say something better. Okay. In fact, if F and G agree everywhere, excluding a finite set of points, then the Fourier series are identical. right? Because right? Suppose you've got two functions and they agree except on a finite set of points. Well, the Fourier series is going to, the Fourier coefficients are going to be identical, so the Fourier series are going to be identical, right? So what does that mean? That asking for pointwise convergence is a priori futile. So that's the gloomy thing that I wanted to say. It makes no sense to ask for pointwise convergence because changing the value of a function at a point doesn't affect the Fourier series, right? So that's not what we're gonna go for, right? Okay, so the questions that we're concerned with are when does this converge, right? And in what sense can we get back our original function, right? We're not going to get it back in a pointwise manner. Are we going to get it back in some other manner, right? Right? Are we going to get it back? So we have to introduce different notions of convergence in order to recover our actual function. Okay.
Professor, so
Yes.
you said that they are identical because they have the same 1/L coefficient?
They're going to have the same f sub n, right? So if I had some g sub n and I have some f sub n that is equal to g except at a finite set of points, right? Then the Fourier coefficients would be the same, right? Because when I integrate g against something, well, g and f are the same except at a finite number of points. Those finite number of points aren't going to change this integral, right? Not going to change the integral at all, right? So in that case, g sub n and f sub n would be the same, right? Even though the functions disagree at these points, right? And so we can make whatever point we want disagreement to occur at, we can make that happen, right? So it doesn't make sense to talk about Fourier, talk about pointwise convergence. Yeah, Thea. Sorry.
Oh.
Go ahead. Thea first.
What kind of integration is this?
This is Riemann integration. Yeah.
And if they disagree at a finite set of points, it's hard for me to imagine two continuous functions would disagree.
But Riemann, remember, we just said that being Riemann integrable means that you're continuous except at a measure zero set of points. So you can have, it's very, you can have, piecewise continuous function is definitely Riemann integrable, right? Because the number of points of discontinuity is measure zero, right? And you can have something much worse than that, right? Susan.
Does f and g need to have the same interval, a and b, or does it matter?
On the same interval, on the same interval, yeah. Okay. Okay. Some important notation. So when we write S and f of x, what we mean is the first one. The first one is the nth partial sum of the Fourier series. Okay, so what we mean by this is the sum from negative n to n. of the Fourier series. Okay. So when we say convergence of the Fourier series to F is going to mean convergence of S of this partial sum to F. In this book, for the next lecture. Okay, and we'll be talking about in what sense, right? Because we don't know in what sense that's going to be. Okay. Here's an important construction. The Dirichlet kernel d sub n means the sum of e to the I and x from n equals negative n to n for x in negative pi. The Poisson kernel PR and theta is defined as summation r n from negative infinity to infinity, r to the absolute value, then e to the I n theta, for theta in negative pi, and r in 0, 1. Okay. Yeah, Edward.
Does this two kernels has anything to do with the approximate identity, or they're just like?
They do, actually. Yeah, they do. Yeah. Yeah. Sorry, I'm trying to think of how to do the last part, because I have something that I've written down as a dumb question, but now that I think about it, it might be kind of tricky. Okay, I'm going to ask it anyway. What are the Fourier coefficients of the Dirichlet kernel? Can you figure out the Fourier coefficients of the Dirichlet kernel? So I have a dumb question, and I have a question labeled dumb, and I have a question labeled non-dumb. We'll start with this next time. Okay, we'll start with this next time. I know I said that we would take a class picture today, so let me use the last 2 minutes to take a class picture. I forgot my gigantic camera, so I'm going to just use my telephone. But